This is the Bullet Cluster, the aftermath of two massive galaxy clusters slamming together. The pink clouds in the center represent the ordinary, visible matter that collided and slowed down. However, the blue halos on the outer edges show the actual center of gravity. By measuring how the cluster's mass bends light from galaxies behind it, physicists discovered that the vast majority of the material didn't slow down at all. It sailed right through the crash. This is physical proof of dark matter. It makes up roughly 85% of all matter in the universe, providing the invisible gravitational scaffolding that keeps galaxies from flying apart. Because dark matter does not emit, absorb, or reflect light, we cannot see it directly. We only know it is actually there because we can clearly observe its massive gravity pulling on the surrounding stars. To determine what it is, physicists run candidates through a matrix of 3 requirements. First, the particle must make mathematical sense. Second, it must fit the cosmic structures we observe. And third, we must be able to physically detect it. A viable dark matter candidate isn't just a placeholder. It has to survive this process of scientific elimination. For years, the leading candidate was the weakly interacting massive particle, or WIMP. It was favored because of the WIMP miracle. A particle with mass and interaction strengths similar to the known forces of nature naturally produces the exact density of dark matter we see today. Experiments like LUX-ZEPLIN attempt to find them using massive fats of liquid xenon buried deep underground. The hope is that a passing WIMP will occasionally strike a xenon atom, triggering a tiny detectable flash of light and a release of electrons. But after decades of searching, these detectors have remained silent. The most common WIMP models are now highly constrained. There is still some hope. Recently, researchers at the University of Tokyo analyzed data from the Fermi Space Telescope and identified an unexplained gamma-ray signal from the center of our galaxy. It's at an energy level, 20 giga-electron-volts, that could be the signature of WIMPs annihilating one another. While it's a compelling lead, the lack of a direct hit in our underground vats is forcing physicists to broaden the search to even lighter and more exotic particles. This has brought the Axion to the forefront. It scores highly on theoretical motivation because it wasn't designed to solve the dark matter problem. It naturally emerges from quantum mechanics as a solution to why the strong nuclear force behaves symmetrically. However, axions are incredibly light. You can't catch them by waiting for a collision. Instead, you use powerful magnetic fields. When an axion enters a strong magnetic field, it converts into a microwave photon. Experiments like ADMX act like a highly sensitive radio, tuning through wavelengths to find that single frequency. Because axions tie so cleanly into established physics, they are currently seen as one of the most promising targets for the next generation of detectors. Other researchers are looking at sterile neutrinos. These are a simple extension of the Standard Model that would interact only through gravity. Unlike other candidates, they are theorized to slowly decay over billions of years, releasing high-energy X-ray photons. Astronomers have actually spotted a faint X-ray line at 3.5 kilo-electron-volts in distant galaxies. If this is dark matter decaying, it would define the particle's mass, but many scientists argue the signal might just be ordinary gas emitting radiation. Then there is the only non-particle candidate, primordial black holes. These aren't made of new matter. They would be ancient black holes forged in the extreme density of the early universe. But observations from the LIGO gravitational wave detector, seen here, along with surveys that look for stars briefly magnifying light, have narrowed the possibilities. We've checked almost every possible mass range, leaving only a few narrow windows where these black holes could exist. This range of candidates shows that dark matter research now spans the entire spectrum of astrophysics, from X-ray telescopes to gravitational wave interferometers. Recently, interest has grown in fuzzy or wave dark matter. This theory suggests the particles are so light that their quantum behavior manifests on a massive galactic scale. In this model, dark matter doesn't act like individual grains of sand. Instead, it behaves like massive overlapping fluid ripples stretching across thousands of light years. This wave-like nature prevents dark matter from clumping into a sharp point, explaining the stable, flat cores in small galaxies instead of sharp density spikes. Wave dark matter challenges the idea that dark matter is a collection of things, suggesting instead that the universe is held together by a macroscopic quantum field. Looking at the evaluation matrix today, none of these candidates, WIMPs, axions, neutrinos, or waves, have been definitively confirmed. However, every experiment that turns up empty is a form of progress. Scientists are systematically narrowing the parameter space, which means thousands of theoretical mass ranges are being crossed off the map. By proving where dark matter isn't, we are squeezing the remaining possibilities into a few highly specific corners of physics. This puts us in a transition period. As engineers at NASA Goddard finish the Roman and Euclid telescopes, we are moving from basic speculation to high-resolution mapping. These instruments will provide enough data on galaxy distribution to help us distinguish which of our remaining theories actually built the universe. Identifying this material will do more than just solve a century-old puzzle. It will finally bridge the gap between the particles we can see and the invisible gravity that defines the shape of our cosmos.